Hello, my name is Skylar Terry, and this is my combined spectral problem on letter J that was given. So starting out, we're looking at the IR spectroscopy, and right away I noticed the 1720 approximate frequency, which indicates the existence of a carbonyl group. And then I also noticed the sp3 CH groups that are indicated by just being below the 3000 frequency mark. And then I also noticed the frequency just above 3000, which indicate the existence of aromatic protons. And next, looking at the carbon spectroscopy, I noticed a peak at about 29, chemical shift of 29 ppm. And this is an indication of a methylene group, as indicated in my table here. I also noticed a shift at about 45, which is another indication of a methylene group. There are a couple of shifts at about 125, which is an indication of an aromatic carbon. And this also goes for the aromatic carbon or the chemical shift at 140. That is another aromatic carbon, indication of an aromatic carbon based on the resources that I looked at through class materials and online materials. And then there's also a 205 chemical shift about that is an indication of a carbonyl carbon. And all of these shifts, I decided the type of bonding environment based on resources through online materials, through UNE, or just referencing online materials more generally. So far, the biggest functional groups that I've identified is the existence of an aromatic ring, and then also a carbonyl. So a carbon atom double bonded to an oxygen atom. And then next I have the hydrogen spectroscopy analysis up, NMR spectroscopy up, and I noticed that there is a chemical shift at about 2.1, and as the spectrum shows, it has a 3H integration, and I saw that I had a singlet multiplicity, so that is an indication of there being no neighboring protons, chemically unequivalent neighboring protons that would cause a greater multiplicity. And then there's a shift at 2.8 with a 4H integration, and this one was particularly useful for the identification of the compound because I realized that it was going to be two methylene groups. It seems like they overlapped and created that methylene group, that group of methylene groups, that being two methylene groups, and created the 4H integration that is present on this spectrum. And then at about 7.2 ppm, the chemical shift, there's a 5H integration, And this was a clear indication of aromatic protons. And again, referencing my materials as to what not only is associated with a particular chemical shift, but the multiplicity seemed to indicate an aromatic ring. And because it's a 5H integration, that is a indication of a phenyl functional group. So combining the phenyl group with the two methylene groups with a 3H integration, that means that there's going to be a methyl group neighboring a carbonyl and two methylene groups neighboring the carbonyl associated with a phenyl group at the connected to the two methylene groups. And so this comes out to be 4-phenyl 2-butanone. And this can also be written as 4-phenyl butane 2-one, depending on which IUPAC standard you go by. So yeah, those are the biggest takeaways that I got from the various NMR spectroscopies as well as the IR spectroscopy. Is the carbonyl compound associated with the methyl group that showed a shift that was associated with being next to a carbonyl. And then the methylene groups, the two methylene groups making up that 4H integration for a 5, it's a 5-4-3 integration ratio. And then finally that phenyl group at the end of the butane chain, indicated by the 4 there. Thank you for listening, and have a great rest of your day.